parameter and statistic. Where does a parameter come from? A population. And then a statistic comes from a sample. So the parameter and the parameter and the statistic that we're going to use today is going to be mu. That's a parameter because that's the population mean. Okay, and x bar because that's going to be a sample mean. Okay, so that's a statistic. This is a parameter. Okay, so a point estimate is going to be a single value estimate for a population parameter. The most unbiased point estimate for the population mean is the sample mean. In other words, we're using x bar to guess what the population mean is. We're using data from a sample to make an inference about a population value, which is called inferential statistics. So we just started inferential statistics. Everything before has been descriptive statistics. Okay. So I'm gonna, I've got this problem from the book here, so you don't need to look at it. I just put it on here. So let's look at an example here. So it says an economics researcher is collecting data about grocery store employees in a county. The data listed below represents a random sample of the number of hours worked by 40 employees from several grocery stores in the county. Find a point estimate for the population mean. Well, this is a sample. So if you average that all together, that's your sample mean. So that is your point estimate. So 29.6. Okay? Now, do you think that the population mean, do you think that the average hours of all the employees in the county is 29.6? No. In fact, you know, we're going to never know it. We're just going to make an estimate that hopefully is close to it or contains the population mean. Okay? So an interval estimate, so a point estimate, just getting a single number, that's not so good. Maybe making an interval that maybe contains that is a lot better. Okay? So an interval estimate is an interval or range of values used to estimate a population parameter. For example, we might take that previous point estimate of 29.6 hours and add or subtract a number to make a range of values that hopefully contains the population mean in this example. So the trick here today is going to be how you calculate this value. Okay, so it's going to be easy because you're going to have data and they're going to tell you the sample mean. We're just going to have to see if we can figure out how to calculate that number that we add or subtract. That's all it comes down to today. Okay. So just kind of doing some preliminary stuff before we get into the problem. It says, why do we call the interval a confidence interval? Well, the confidence that we have that the population mean, mu, is in the interval is based on the width of the interval. The wider the interval, the more confident we are that the population mean is in that interval. If you have your book, open it up to A16. I want to show you how we're going to calculate a value in the formula for E. Let's do this. Let me show you what E is. There is a formula for E. So here's your formula for E. So page A16. Not 816, A16. So here's your formula for E. It is Z sub C times sigma divided by the square root of n. Z sub C times sigma divided by the square root of n. We're going to try to understand that here. Z sub C times sigma divided by the square root of n. Okay, here's your confidence. The confidence intervals that you make today are and they might throw a weird one at you every once in a while, and I'll show you how to find it. But for the most part, you have a 90, 95, or 99% confidence interval. Now, if those are your confidence, then there's specific values for Z sub C. They're right on your bottom of your paper on page A16. So they give you 80, 90, 95, and 99. Well, the most common are these. So if you have this as your confidence, then that is the number that's going to go right in there, 1.645, or 1.96, or 2.575. Okay, so here's where they come from. And if you were to, and I think there's one like this on your assignment today that you have to calculate, here's what they come from. And I'll explain this more tomorrow. But if you have a 90% confidence, then really what you do is you're calculating that Z is the Z score that cuts out the middle 95%. Or excuse me, the middle 90% in this case. So if this is 90, what's that? 5, right? And so this is 5. And so if you looked up the Z-score that cut off the bottom 5% from the upper 95 or the top 5 from the bottom 95, it would be negative 1.645 and positive 1.645. And so then you just ignore the negative, and that's your Z-score. Okay? This is called your critical value. And you use that critical value when you calculate the error, the E. Okay? Now, to make a confidence interval by these methods, well, this is a no-brainer because you got it in the formula, okay? And then you need to make these requirements. The sample needs to be random, and you have to know the sample size, obviously, because that N is going to be in there as well. And then here's the deal. What does that Z mean? What did we say when we have a Z distribution? It's really a normal distribution, right? Okay, so when do you have a normal distribution? When you're talking about samples. When the original population is normal, then you're going to have a sampling distribution that's going to be normal. Or if your original, or if your sample size is 30 or more, then you're going to have a distribution of means that's going to be normal. So I'm not going to get into every little detail of this, but I do want you to understand this, okay? That we're talking about sample means, right? We're going to take a sample and we're going to use the sample mean to help us calculate the confidence interval, right? Well, if we're talking about sample means, we need to understand when are the distribution of sample means normal. When the original population is normal, or you take a sample of size 30 or more from something that's not normal, okay? So it kind of relates to that central limit theorem, okay? And we'll talk more about that tomorrow, but we're dealing with sample means. So we need to know when is that distribution of means normal, okay? So E is the margin of error. It's called that. So they might tell you that the margin of error is a certain value, or they might say it's an error of estimate or an error tolerance. So just if you hear those terms, that's E.
Where did you get the critical values from?
They're in the table in your book.
So I'd
Or-
90%.
Or you could take out the middle 90% and then the z-scores that would be that are that guy right there. So if you looked up 0.05, you should see that value for the z-score. Okay. So I think they do give you they say calculate the z-scores for the 97.5 confidence interval. So you might have to do that today. So draw your picture, carve out the middle percent, put a little percent to the left and a little to the right, and then calculate the z-score. Could you use your calculator to do it? Inverse normal. Put your percentage and you got it. Okay. So let's try a problem here. We'll find a confidence interval for this, okay? So this is that example. You don't need to look in your book. This is it right here. So it says a college admission director wants to estimate the mean age of all students currently enrolled. So again, we're going to have to kind of say that he doesn't have access to all their ages for some reason. Maybe it's not a part of their information. I don't know. And so then let's say that he does this. It says in a random sample of 20 students, the mean age is found to be 22.9. From past studies, the standard deviation is known to be 1.5 and the population is normally distributed. Construct a 90% confidence interval for the population mean age. Okay? So give me a letter that equals.
S.
N for sample size, right? Okay. How about this guy here? Well, let's read it. Let me read it again, okay? It is X bar, right? Because it says in a random sample of 20 students, so the sample size is 20, the mean age of the sample is 22.9, so that is X bar. From past studies, the standard deviation is known to be 1.5, so that is sigma. That's saying that we do know the standard deviation of this distribution. We're saying it probably hasn't changed, but maybe that we think the mean has. So we're trying to get an interval that's going to hopefully contain mu, which is unknown really for us. Okay. Okay. So what's z of 90% going to be? 1.645. You should be able to put that into the formula and calculate E. Okay? So Z sub C times sigma over the square root of N. So you should get about 0.55. Have you made the interval? No. What do you have to do? Right. So now, sometimes they might do it like this to name the interval, or maybe we want to actually subtract 0.55 and add 0.55. So that would put it at 22.35 to 23.45. It just kind of depends. They might give it to you like this. I think I would actually prefer that we might calculate the interval from the low to the high. Okay. Okay. Here's what I want you to do. Is I want you to calculate. This is the 90% confidence interval. I'd like you guys to calculate the 95. you get 0.66?
Yeah.
Okay. So 22.24 to 23.54 would be your 95% confidence interval. 5.6?
Yeah, you
Okay.
other
Let's see here. 6 here, right?
Yeah.
Okay. Now, here's an important point. Which one's wider? 95. And in general, that's the case. What did I say at the beginning of the period? I said as your confidence increases, what is going to happen to the z? It's going to increase, and what's going to happen to the width of your interval? It's going to get wider. Okay. Now, does n have a play on it as well? What would happen to e as this number gets bigger? As the denominator gets bigger, e would get smaller. So as your sample size were to increase with everything else staying the same, then your interval is going to get smaller because like you got more information. Okay. So just to kind of summarize here, if we take a sample from a population and make a 90% confidence interval, again, sometimes it might be one sample mean value, sometimes it maybe would have been another one or another one, okay? But 90% of the time that I make a confidence interval, what's going to happen? Right, the population mean will be in that interval, that percentage of the time. So you can write that down and let's look at it again just to make sure you understand this concept. So if we take a sample, which might be one value or it might be a little bit different depending on the sample that you take, okay, and make a 90% confidence interval, 90% of the time that we make that confidence interval, it will contain the population mean. Okay, write this down. Put mu right there. And go x bar minus e to x bar plus e. What percent of the time is mu going to be between there and there? Well, it depends on the confidence level that you've made. So it equals C. Make sense? The probability that that guy is between there and there is going to come up at whatever confidence level we made that interval of. Okay, we got one more thing to do. Anybody got a question so far? Okay, so the next one, what we're going to do is we're going to make a formula for n. Okay? So if I took this equation that we already have and I solved it for n, you would get this. So write this down somewhere. Try to include it on your formula sheet at some point. N, the sample size, is going to equal z sub c times sigma over e. That's your error tolerance. Squared. Quantity squared. So you don't want to have to go ask 1,000 people if you can ask 50 people, right? To get the information that you need for the problem. So let's take a look at this here. So that economics professor where he wanted to calculate the average age of his students wants to estimate the mean number of hours. Oh no, this is a different one. Where the grocery store employees. Okay, so how many employees must be included in the sample to be 95% confident that the sample mean is within 1.5 hours of the population mean? So what's this? What's that 1.5? Within 1.5. That's your error. That's your maximum error allowed. So that's E. So just calculating n, it's going to be z sub c. That? No, the z-score for 90%, which is? Right. 1.96 times sigma divided by your air tolerance, which we said is 1.5 quantity square it. So work that out and determine n. You got to do a little thinking here on this. So do the calculations and then determine the sample size. You have to think about it a little bit. If I told you the answer was 106.5, what would you say?
You can't serve a half.
You can't have a person. So you got to round up 107. So this formula really has two parts. You got to calculate this value and then round up. Can't have a fraction of a person in your sample. Okay, a couple quick things here now to finish up. What confidence level produces the widest interval, do you think? 99, right? If x bar is 54 and e is 7, draw your confidence interval on the number line. Right? So your confidence interval is this here. What's the center of this interval and all intervals? The mean, the sample mean. Because you're going to go this guy plus E and this guy minus E. So that middle, that point estimate, is going to be the middle of your confidence interval. What's the width of this interval and all intervals? Nope. Nope. What's the width of this interval? How far? Right, it's 14, which is 2 of those E's. Okay, so from there is E, and from there to there is E, so the width is 2E. Okay. So the assignment, I'm going to do an activity with you tomorrow to kind of reinforce this, and I might talk about a little bit more. And that'll be all due on Monday. So I'll finish up, you'll continue to work, but get a good start on it, and then you'll have some time tomorrow to finish.
Just the circled ones?
Well, I would think that you should have at least those done for tomorrow. Do all of it for Monday.